Today we're going to talk about, we're going to present the waves in elastic media. We're going to touch a tiny bit of the fascinating world of the physics with waves and elasticity. My name is Mahdi, and this is my classmate, Matthew. This is going to be the roadmap of what we're going to cover today. First of all, is the motivations, what motivated us to study into this thing, into this field about waves and elasticity. Then we're going to drive an equation from a simple string to find the density, linear tension, and elastic force. And we're going to see what happens if we add extra force into it. And there's some videos. We're gonna have a hand-on model video analysis on the experiment with it. And there's another experiment with it, which is the resonance in air medium. And there was another experiment with it. And we're gonna talk about possible improvements and potentials we can do for the other experiments and future research. At the end, we're gonna talk about applications of resonance and standing waves after we talked about those terminologies. When it comes to motivation, elasticity is nature. It's everywhere. It's in the ocean. It's in the air. I'm talking. The sound is moving into the air. It's elastic. Even the ground beneath us is elastic. And everything wants to push back. These pushbacks rely on elastic properties that governs them in waves. These waves have different behaviors that have their own behaviors, and that's what we study. The concept of wave reflection, I don't know if you have ever been in a canyon and shouted something. You can hear your voice coming back to you. You can use that to measure distance. You can use that to study material. But what we studied today was, what if the force exceeds the system's limit? What if there is too much external force? One motivation we had was the Tacoma Bridge. This one was what my physics teacher used back in my country to talk about resonance. And actually, there was a misconception. This Tacoma Narrows Bridge was built in Washington in July 1940, and it was collapsed a few months after, in November 1940. And many engineers at the first talked about it was the rhythmic marching of the soldiers that made the bridge collapse, because that rhythmic marching was creating a wave that was adding to the natural frequency of the bridge. And the resonance happened and the bridge collapsed. But that wasn't the issue. The actual thing that caused this to happen, which was just at that time, was the wind with the 42 miles per hour, nothing insane, blowing and resonating with the natural frequency and resonate happening, and this whole system breaking. Now my friend is going to talk about the first experiment with it.
Okay, so we'll start by trying to derive the general form of the wave equation. So we're going to imagine that we have a string and it's tied to a fixed end, and we're holding the other side so we can exert an external force. And so if we move it up and down, we can see that displacement will vary with time and space. And so we're going to start off with kind of like a mathematical introduction, and then we'll get into a bit of a more visual conceptual understanding. So we're going to say, suppose we have a wave propagating in one dimension where the vertical displacement u is a function of time t and position x. So we can say u is a function of x and t. We're going to let time be held constant, and that means that u will just be a function of x. We say that we have a wave, so f of x must be oscillatory. So for any point x, there exists a nearby point x plus delta x, where delta x is infinitesimally small, where u of x must be less than u of x plus delta x, or u of x is greater than u of x plus delta x. It just depends on the situation. We're going to only consider the first case, but it doesn't matter which case you consider, you get the same equation. And so what we're saying is we have a wave where vertical displacement varies with time t and position x, which will be moving from left to right, and we're going to hold t constant, so then we get like a snapshot of just how vertical displacement will vary with x. So that's the bottom. Then we're going to zoom in really close on this snapshot, and we'll notice that there are 2 points next to each other, where the vertical displacement is greater for u of x plus delta x than it is for u of x. And this works anywhere you zoom in on the wave. This will always occur where there's a nearby point where this is true. And now we're going to bring in the elastic force. So elasticity governs that for these 2 points, there exists a restoring force T, which in the case of the string would be tension, that is tangent to our wave and will always oppose vertical displacement. So it's going to try to pull this string back to an equilibrium position. Because we're working with only vertical displacement, we're going to take the vertical component of this tangential force. And so we'll take u of x to have a vertical component of negative t sine theta 1, and u of x plus delta x to have a vertical component of t sine theta 2. And even though it looks like it's a straight line, because we zoomed in so close, it's important to recall that theta 1 is not equal to theta 2, because there is some slight curvature. So in this reference frame, there's a couple assumptions that we need to use. One of them is that the vertical component of this force is basically equal to the partial derivative evaluated at the point we're at. Now we're going to use Newton's laws of motion. We're going to add up these forces, which we see on the first line, and then we're going to factor out the restoring force tension. And then we can see that we can recall that the second partial derivative is equal to the first partial derivative evaluated at x plus delta x minus the first partial derivative evaluated at x all divided by delta x. If we move that delta x over to the other side by multiplying by delta x, we can see that it's basically equal to the line above. And so we get that everything we did is just equal to the tension force multiplied by the second partial derivative multiplied by some delta x. Okay, now we're going to take a step back and think about what happens if we take x to be constant. Then we get, if we add forces in the vertical, on that affect vertical displacement, they must be equal to the mass times the acceleration, which is the same as saying mass times the second partial derivative of the vertical displacement with respect to t squared. Mass is equal to linear density times some delta x. And so now everything kind of works out nicely. If we set these two forces equal to each other, and then we can cancel delta x on both sides, we get the general form of the wave equation, which is basically telling us that the acceleration at any point on the string in time due to the restoring force is proportional to the curvature of the wave at that point. And that kind of makes sense conceptually as well. So now we're going to introduce an external force density. And the reason we say force density is because we're treating the string as sort of like a continuous object. So we have to choose for some length on that string. And this external force density is driving the string's motion at any one point. So how did the string become displaced in the first, or how did it get displaced in the first place? It's because you're moving the string up and down with your external force. So finally, we say that acceleration of the string is due to the restoring force, which is proportional to curvature, plus whatever external force we put into the system. So rearranging, we can actually solve for that external force and say that it's equal to the difference in acceleration and curvature, or is proportional to that difference. This is the experiment that we have. In the middle, we have a string, which is connected to one semi-fixed end with a vibrator that can move up and down. And then on the other side, we have a mass, which keeps the tension. So we have a fixed end. The distance between these two fixed ends is 2 meters. So the string is stretched 2 meters. And we marked on the background what 10 centimeters is, so we could do a video analysis. In order to do the video analysis, we need to determine what our parameters are, which we're going to use in the equation. So we decided, or to get linear density is pretty easy. We just need to weigh a segment of the string and then plug it into this equation down here, which is mass divided by length. And we got that value. And then to find wave speed in the medium, which is v, and really this is just depends on what kind of medium you have and how densely packed the particles are. We can do frequency times wavelength using harmonic modes. And we'll get more into this later, but it's really pretty simple. And then finally, we need a way to solve for the derivatives numerically. And the reason we're going to do it numerically is because to be able to solve for the derivatives analytically, or to solve this equation analytically, you need like an extensive knowledge on partial differential equations. and initial value problems, and then also having fixed ends, and we can't do that. So we're going to use something called the central difference method, which basically allows us to approximate these derivatives visually. And so finally, we can conduct video analysis and then find what the external force density is for varying time. This is just a short video kind of showing what happens when we turn on the vibrator and increase the frequency. We can see some small displacement, and then around here we can see much larger displacement. And so what we're seeing is that the frequency is approaching one of the third harmonics of the system, and that's why we have 3 peaks or antinodes in wave displacement. Oops. So after conducting video analysis visually, which is a horrible thing to do, and it took a very long time, we were able to actually plot force density as the frequency approached the third harmonic, and we can see right around time 11.2, f of xt, which is going to be newtons per meter, kind of shoots up. And this is what we're seeing here is basically the system is starting to resonate. And so right here we have just force density with time, and here I took an absolute value so we could kind of get a sense for the scale, and we see about 10 newtons per meter force density around 12.2 seconds, where it's basically 0 before.
My friend talked about resonance. So let's go over some terminology of what resonance actually is. So waves amplitude, when they reach an end, the fixed end, it's going to reverse and invert over the equilibrium of x-axis, and it's going to switch the direction. What is harmonic frequency? This occurs when the medium length is an integer multiplier of the half wavelength. I'm going to show you these in the diagram and images I've got. And what's the superposition? It's a principle that these forces, these amplitudes of different waves, when they reflect, are either going to add up. They're going to either add constructively or destructively. Standing waves happens when these harmonic frequencies, which happens when the half wavelength is going to be an integer multiple, reflections, so they go and reflect back, causes constructive interferences. So they add up. These amplitudes is going to add up and constructively, so we get the standing waves. So the nodes and antinodes are not going to be changing over the x-axis. As you can see here, the wave goes, hits the fixed end, and then reflects. And here, the two amplitudes are going to cancel each other out. The antinodes are going to be at the same spot, stationary, and this is going to be the standing wave. There is no energy transferring in this one because all the energy is going to be just into that amplitude. But in resonance, that happens when the new energy, when the external force, when the new frequencies that we push into the system is going to match the natural frequency. That's when the energy and amplitude is going to increase and increase over time. That's why the glasses break in the movies when the opera singers start to sing. This equation can be used in a different model with it. This is the second experiment with it. Why this equation works here? Because we have a space for our medium that is contained and it's in a tube. But in this one, we use the fixed frequency compared to the other one. Here, what we changed was the medium length. By changing the medium length and having the fixed frequency, we found when the sound was peaking, when the resonance was happening, and we found harmonics number in that one. So for this experiment, we had the resonance tube. We used the 5,000 hertz frequency, and we measured the length of the tube as we were like pulling down the other end. We were measuring the length when the resonance was happening. How we found out when the resonance was happening? That was when the sound was peaking. And we used iPhone recording to see, and this is where the resonance is happening, to see when the resonance is happening. So if this was the sound wave, this is the half length of the sound wave. If this dead end was at here, we could have the resonance happening. So this is going to be the harmonic number one. We just kept going and kept going. with different harmonic numbers. And using these equations, the second one, 2 times the medium length over the number of harmonics, which gives us the the wavelength. And the first one, which is the speed, is going to be equal to frequency times the harmonics. As you can see, the number of harmonics increasing gave us a more accurate speed for the air. And the speed we got was 333 meters per second. And the actual speed of air is actually 343. So if we had more harmonic numbers, maybe we could get more accurate data. And using the bulk modulus of elasticity, a bulk modulus is a constant for each substance that shows how resistant they are to compression. Having that and finding out the speed, we put it into that formula, and we got that the density of the air is going to be 1.27 kilogram per meter cube. But the actual speed and density are here. So we did a bit of miscalculation and had some error, but basically by using a frequency and a tube, we found the density of the substance and the speed of it.
So we kind of ran out of time at this point, but some future research we would like to do with sound is we want to find a way to record data for numerical calculations like we did with the string. And really this means we need to be able to observe second derivatives like curvature and acceleration, which we don't know how to do yet because sound waves are visual, right? We also want to, like we did with the string experiment, demonstrate the concept of resonance, more intuitively by plotting external force density as the length of the tube approaches some harmonic length.
And here this was actually the first experiment we wanted to do. We wanted to see the sounding waves happening in the water medium, but this didn't happen because there was some limitations. The speed of waves in water was 3 times faster as it was in the air, and we couldn't notice the curvature. Maybe we had to use a different medium length. Maybe we had to use different frequencies, but that's something we can do into future researches. And resonance is not just a theory. There is a lot of applications. The sounding waves and resonance happens in musical instruments, in medical imaging, ultrasound, MRI, and seismology, predicting and measuring the strength of an earthquake, and communication systems, even in your ear. Thank you guys for listening and paying attention and being here. That was our presentation.
Questions?
Sure. You gave a value for density of air, and that's a thing that depends on temperature and other things. So the number that you stated, it should be this. How did you determine that?
Yeah, so we used, we made a couple assumptions. When we said, you can go to the slide real quick.
Which one?
Very last, it's kind of like one of the last slides, farther down. You're talking about for air, right?
No, actually, it was up earlier.
Oh, it was?
So it was near the end of the
Yeah,
presentation, but you had it on the screen earlier.
This one.
Yeah.
That one right there. Rho is 1.293.
Yeah, so we took, we actually looked up bulk modulus.
Yeah, we got the bulk modulus of air at
STP.
Yeah.
Okay. I missed the STP.
Yeah.
Right. And how close to the STP was it?
We made an assumption it was at STP. We didn't do that perfect measurements, but this is what we got for rho, and this is the actual rho. So it was kind of close, but we didn't get the speed as accurate as it was as well. We got 333, but the speed of air is actually that, so that could mess up the results. But we got the bulk modulus at STP.
So do you know what the temperature is in STP?
It's 25 Celsius.
So room temperature.
Yeah, it was about room temperature. And we were at the other Miracoast campus, so close enough to sea level, but we'll say to the good enough, I guess. This is more, we didn't really go very far into the resonance tube. We more developed sort of some basic experimental ideas. Mm-hmm. But the experiment we more had fully developed was a string experiment. And the reason we kind of developed that one so much is because it sort of expands to these other experiments quite nice. The only thing we need to work on now is sort of like being able to understand the limitations that comes with these, you know, working with air and then working with water. Yeah.
Okay.
Great question.
Yeah, thank you.
Anyone else?
Sorry, I just came in like maybe halfway through your presentation, but I was just interested in how you guys like constructed like the machine that like, you know, made the string. Like, was this something that you had, or was this something?
Yeah, this is a pretty common experiment to, I mean, I don't know if they do it at Miracosta anymore. You might know, you've probably seen this experiment, right?
I have seen that.
Yeah, it's a pretty common way to see like, to demonstrate resonance, because when you turn up the frequency, you can see how you don't see much amplitude at all of a sudden it shoots up, and you can literally count how many peaks and valleys there are. So this is a really common way to show resonance, and it really helpful for us to understand it as well, because trying to do it in air and water, it's not so like visual, you know. It's,
right.
Yeah.
So you had to go for like frame by frame and like
It was on.
how long did that
That took like 5 hours, maybe.
5 hours?
There's a lot of
for an
data.
8-second clip.
No, we actually, the clip I had got like corrupted after, I guess. So
I recount.
I didn't, no, I used a longer 20-second clip. I probably should have used the 8-second clip or 2-second clip. I could have used a really short clip, but I didn't think about it much. But yeah, it'd be nice to use, this would be a good thing to use AI for if it could do that or something. But yeah, you have to basically, this is the equilibrium axis. You can see this little dot there, and to estimate the second derivatives, you have to go frame by frame. And so you pick a frame and you can oscillate about that frame and record what the displacement is from this horizontal axis. And you plug that in. I used Google Sheets. You can just plug it into the formula we had, and using the central difference method, and then kind of comes out to giving you the right units and everything. So, but yeah, it's not fun to do. So
Room for improvements.
Yeah.
Any other questions? All right, that's it. Thank you, guys.
Thank you guys.
Thank you again.